presentación. Voy a hablar en inglés, pero yo puedo también hablar en español para preguntas. So Alberto gave a good background on some of the faults in Puerto Rico. But I'm going to talk more about the onshore risks, primarily with the ground motion work that I've been doing a lot with work with Jose and the Strong Motion Network, looking at ground motions in Puerto Rico, as well as talking about the offshore, and specifically about tsunamis, because that is part of the engineering code in the ASC E7. So I'm going to start talking about our ground motions. It's going to be separated kind of ground motions and offshore. This is ground motion studies. This is with PRSN, the Strong Motion, Puerto Rico Strong Motion Program, and as well as working with the USGS. Now, ground motions, as engineers, you know, are quite important because ground motions are what impacts your buildings. In order to look at the ground motions, we also need to look at ground motion prediction equations. So obviously, I think for this room, most of you guys know what this is. You have your dependent variable related to intensity measurements, your magnitude, the geometric attenuation, our inelastic attenuation, our side effects, and uncertainty. So this is our general ground motion predictions equations. This is originally from Bohr and Joyner in 1982. This equation has not really changed since then. Now, recent work that has been done by Diego Carlos with the Strong Motion program in civil engineering, we actually now have data-driven ground motion prediction equations for Puerto Rico. And this is important because before we did not have data-driven ground motion prediction equations. And now we do. That is published in a thesis. We're trying to hopefully get this published somewhere. But we based off of essentially the USGS system, where we have taken a number of earthquakes. We did actually desample the earthquakes in southwest Puerto Rico because the 2020 sequence would then dominate our data set. So we did some desampling in southwest Puerto Rico to have some balance with our offshore and our onshore events. So we select our events, we process the ground motion records. We do unit magnitude unification because in any earthquake catalogs, including the PRSN catalog, you have different types of magnitudes. You have moment magnitudes, local magnitudes, and duration magnitudes. In order to use them in one system for creating a ground motion prediction equation, we had to perform a unification when we transferred our duration magnitude and local magnitude into our moment magnitude. I know there's a little geophysical jargon in there. It's just the idea is that we have to have everything in the same system so we can compare what is the amplitudes between these two different magnitude earthquakes. And then we do a functional form of regression analysis. Ironically, we looked at a regression analysis. Diego, when he did his work, he actually found the most simple regression gave us the best answer. So we did actually get the ground motion prediction equations. What this chart shows, this is from Diego's thesis, where you have, here we have records for MW with hard soil. And this is our GMPE, the red line is the GMP from his study. We have different GMP. The green dashed line is what we were using in Puerto Rico before, the Montes and Atkinson. And then you have an Acker and Bomer and a Zhao et al., which are the dotted and dashed lines. What you should want to note is the Puerto Rico's ground motion prediction equation is very similar to the Zhao one. And that makes sense because this one, the Zhao one, is for the Japan subduction zone. So essentially, when you're looking at Puerto Rico, our ground motion prediction equations are looking at essentially similar ground motion prediction equations that you expect in a subduction zone. So we are part of the subduction zone in Puerto Rico, Japan's subduction zone. And we have very similar ground motion prediction equations. And the dots here are our records, our data measurements off the records. You can look here that most of our records fall near the line. But you do have some excursions from the data. And those excursions are most likely due to things called site effects. This is more obvious here. Here you have the 95% our standard deviation. So if you look at our records within standard deviation, we say the equation works pretty well. But then you have a point outside our standard deviation in both these examples. Both these examples, I believe, are from Utuado. And what that says is there's something going on at this site that the ground motion prediction equation is missing. So if you're thinking about our equation, what really is the most variables that are site-specific is what we call the site effects. So the other work we've been doing is looking at our site effects. And this is an example from the 6.4 in 2020, where you can look at this. This is the same plot I've written in just two different ways, one using the logarithmic scale, one using just a straight PGA scale from the CESMD and the Puerto Rico Strong Motion program. And the one thing that's worth noting is your PGAs in Utuado, which is in central Puerto Rico, are something at 0.5. We're closer to the epicenter, and you have lower PGAs. So it's a very large sign that there's something going on in Utuado. There's something going on in that site that's causing large amplifications. What I think is a combination of topography, basin effects, and the actual site effects. We'll actually be going out there Monday to do some work. So when I'm talking about site effects, what you're really talking about are things like amplifications. And there's two types of amplification. I'm going to talk a little bit more about the soil-based amplification, but in the Caribbean islands, you also have topographic amplification. So when you talk about amplification, you essentially go from solid bedrock, and as you get into slower, poorly consolidated sediment or water saturated sediment, the amplitudes of your seismograms and your seismic waves gets larger. And if you have larger amplitude in your seismic waves, you have more ground shaking, which will then, in fact, impact your structures. So to look at soil amplification, this is an example from some work from my master's work from Project Brunat, again with civil engineering, is here I have, just in the Mayaguez area, some sites, and these are actual seismic records. All of these stations have the same instrumentation, so you have the same seismometer and the same digital recorder, so they should be seeing the earthquake the same way. The top two sites, one in Omegueros and the other one in just around the Omegueros-Mayaguez border, are on bedrock. The other two, this is on the biology building at the UPRM campus, and this was at the MYO3 strong motion site. You may notice is comparing the bedrock sites to our non-bedrock sites, you have a much larger amplitude. And it's a strong sign that amplification is very important in Puerto Rico, especially when you're considering the scale of this, you're talking a few kilometers. And to be honest, I did not put in here the MYO12, which is also a bedrock site. So the bedrock site to the biology building and the PRSN is less than a kilometer, and you're going from bedrock to soft soil. If we're looking at soils, you need to also know about your soil types. So this is courtesy my current graduate student, Sherry Lynch. It's from her undergraduate work. These are some of the sites that we did work with the USGS. We were looking at where we went out and got what we went out and did active source surveys with both P wave and shear wave sources. This is actually a picture of Jose at one of our dam sites. I think that was CELP. Where we actually went out, this showing what the line is. We put out a line of geophones. We use a hammer source. This one looks like it's a vertical source. Hammer's going down. Shear wave source, you're essentially standing on a piece of wood and then hitting it from the side. We collect the shear wave and P wave data, and then, that's a video of Jose actually stunning the hammer, creating our data. Then we do what we call multi-channel analysis of surface waves. And the first thing you do is you pick your PNS arrivals. This is the actual record we get out from the field. You can tell here this first geophone looks like it was not working or was swamped by the actual source of the hammer. But then you can pick your P wave or P or S wave arrival, depending if you're using the vertical or horizontal geophones. And then you can, after you do a calculate and pick your Rayleigh dispersion and Loveloy dispersions, which is what you're showing in this middle ground here. Here you're kind of picking where you're the reddest, there's the most power at certain frequencies. And then you can convert this to get a 1D velocity model for your site. And your VS30 that you commonly use in engineering is essentially the average of this model over the top 30 meters. And this, however, I will note that this is a geophysical method. I make it look simple here, but it does require a lot of geophysical experience. So if you want to have a site response, I'm going to say this again, and over and again, you need to have a geophysicist. An engineer cannot do this. This requires specific training, like I can't design a building. This requires a geophysicist to do this type of training. There are some tricks. But moving on, that was one way to do site effects. We're now moving on to a new methodology in Puerto Rico. And this is essentially spatial autocorrelation of microtremors. So we now have nodal arrays, these are small seismometers, which have a battery, a seismometer, and a GPS all in one. We put these out, bury them into an array. This is an example from Francisco Hernandez, made a plot of an array we did at a site near Mayaguez. You put out your nodal size model, whereas this one takes 11 to do. You can add a 12th one in the intersection of the lines if you wish. You put out the minimum of 11 nodals into a triangular type array to essentially generate 3 circles of distances. And this is an example from the field where we were last week, burying out some of these nodals in the field. You bury them in the hole. You turn them on, and you leave, and you pray. And you come back, and you have an answer. And then when you get to the retrieval field, you can do a Bayesian process. This is from my colleagues at University of Utah, who I'm doing this project with, Sirio Pachi. This is from his paper in prep, where you have your array, you get your SPAC amplitude for a series of frequencies, and then you use a Bayesian analysis to figure out where the likely interfaces are. Here you have an interface at 10 meters and an interface at about 25 meters. This is with the noise. This is an example excluding the noise correlation. You actually get more complexity. So we are actually we are working primarily with our noise correlations. So you get a number of interfaces, and then you get your most likely, your most probable velocity model. The advantage of these Bayesian ones is, unlike with the other traditional surface wave analysis, you can also get a rough error and understand how good is your model based for the data. When you do a traditional inversion process, you have ways to evaluate, yeah, does this work or does it not work? But there's a lot more interpretation and personal experience that goes into creating those models. The Bayesian analysis makes it a bit more computational, but it also gives us a much larger idea of how good the data is at a particular site. So essentially, your end product is the same thing, but the advantages we think of the nodals is you can put them out. The nodals take about 2 hours to deploy the array, and we come back a few days later, retrieve the array, and then run our analysis. And we have error bars. So this is a project that we're currently working on. We are going out to Chihuahua on Monday to put out a set. I think Melissa's going out to another site on Tuesday to put out our other set. So this is something we're currently working on. And currently, I'll say part of Cherry Lynn's project is that we are looking for sites. So if you're working as an engineer and would like to have a site done, please drop us an email, and we'd be happy to consider putting out the instruments for a week at your site, because it is part of what we call collective impact. Our data is only as good as it is useful to our stakeholders, of which you are here today as engineers. You are our stakeholders. So I'm going to switch gears. That's essentially some of the work we've been doing in ground motions, and that's continuing work. I'm going to start talking about probabilistic tsunami hazard analysis. Probably not something you thought I was talking about. Oh, faults in Puerto Rico, earthquakes. When you're talking about earthquakes in Puerto Rico, you cannot forget about the tsunamis. And this is something I'm working on with Honky Theo at AECOM. This is actually sponsored by the National Tsunami Hazard Mitigation Program. They're going from our deterministic models to a probabilistic tsunami model for a hazard assessment in Puerto Rico. Now, why do we care? We care because we have ASCE 7, which is for the engineers here. This should look somewhat familiar to you. It is a building design that covers things for general earthquakes, structural earthquakes, wind, snow, flooding. It's every 6 years it gets updated. It's part of our international code. And there are other standards available such as ASCE 41, but ASCE 7 is what includes the tsunamis. So what is a probabilistic tsunami hazard analysis? Well, one, you start with a comprehensive sense of source models. We already have that because the PRS has been working on that for almost a decade, I think, at this point, or over a decade. We have also the good things, the advantage is that you have epistemic uncertainty based on its probabilistic nature. We include the natural variability of processes and the limitation of our ability as science to understand those limitations. And it's consistent with other hazard processes, such as earthquake maps. You have our seismic maps. Those are based on probabilities of PGA extending into the next 10 years. We move to something similar to that with tsunamis by using this probabilistic tsunami hazard analysis. For that, we also get the mean and median hazard. And you can work on other parameters, such as momentum, flow velocity through possible buildings. And we look at typical returns of engineering interests. So rather than the geologic timescale, we start thinking on the engineering timescale of the 72 to 2,500 years. This is an example of what's in ASCE 7. So essentially, you have your sources and your frequencies, your tsunami generation, your ocean propagation, offshore coastal velocities, and then you start going into the more engineering side where you have the interaction of these with your structures. So if you're looking at here, when we talk about the PTHAs, they're talking about here, we're talking about our generation for both local and distant sources, our offshore propagation, and our offshore open ocean propagation, our offshore tsunami amplitudes. And if you're also looking at the coast and inundation flow models, basically this is now input for our inundation and flow models, which are done by NOAA, PRSN, our local scientists here. We're talking, these are such as your flow models, looking at what's the flow of water going to be due to tsunami in the bay in San Juan. So how is this going to impact our shipping? Now, if you look at to compare it to our seismic hazard, in the seismic hazard, we have your magnitude and location of recurrence, and then PTHA, you have magnitude, location, recurrence, and amount of slip. So how big of a tsunami can this be generating? You go to PHA, you have your ground motion prediction equations. Our PTHA, we're talking about law and model bathymetry, numerical solutions for using finite difference. And then you can go, then you have your integration. Here, for GMPs, you integrate to a site hazard. For PTHA, you can integrate to an offshore hazard. And then if you're going to comparing to the PSSA, you have your nonlinear storyline analysis. You do the nonlinear numerical analyses as well based on these, find analytical and empirical relations. So for Puerto Rico, I'm just showing you the subduction zones here. We have the Puerto Rico Trench, Antilles, the Southern Caribbean Deformed Belt, the Northern Panama Belt, and the Mercer's Trough. So I'm going to take an example of how we start approaching this. We start with a segmentation model. This is coming out of a Powell Center meeting. We had all the experts, including local Puerto Rico experts there. And based on the experts meetings, you have the Muertos Trough. Debate if you're going to have single segment or two segment is more probable. Muertos East, Muertos West, to Muertos East and West. And we kind of go down to different scalings and our probable magnitudes off of that. This is actually coming from the Powell Center. This is just the Muertos Trough. This is a working model. This may change between now and when we publish. But this is what we're starting with based off of what came out of the Powell Center meeting. What you end up getting is essentially, you end up with a maximum wave height versus recurrence years, and your amplitude in meters versus rate of exceedance in years. So you end up with very similar curves as you do with the traditional seismic hazard. So this is empirical. Note this is not for Puerto Rico. This is for the West Coast. But these are the type of curves you'll end up getting. I want to do kind of end with like a couple of advertisements of coming attractions. This was I'm going to start with the Presentado experiment for the Puerto Rico subduction and tectonics seismic investigation. Thank you so much. So this is a large onshore-offshore experiment. We got our data in November, December of last year. This is the first experiment of this size in Puerto Rico in its history. To show you what it is, what we did, we had land stations that I installed, some of which the broadbands are still out, through central Puerto Rico. And we had both an OBS experiment and a multi-channel seismic experiment using the MV Landsat, where you have the ship as a source, and then you'd have then you'd have recorders coming off the back of the ship, as well as OBSs recording that data. The key here is with this experiment, we actually had what we call ultra-deep OBSs. Normal ocean bottom seismometers have a crush depth, meaning that it could go to about the edge of the Puerto Rico platform. The ultra-deep OBSs that we got from Germany meant that we were able to, for the first time, place seismic instruments at the bottom of the Puerto Rico Trench. So this data will be our first actual direct images of the Puerto Rico Trench. The MCS, I don't get any pressure to show you this today. We do actually have some of the original MCS images from the ship, the raw data. And the raw data, yes, you can see the subducted slab. So this is the MV Landsat that we did the work. It was based in San Juan in November, December. And this is going to be coming attractions. I'm already beginning the process of the land data, and we'll be processing this over the next 2 years, so stay tuned. The other thing I wanted to say, that this is something that it's kind of in the incubator stage. This is actually a grant that we're kind of working on right now based on UTEP. UPRM is hopefully going to be a subaward or a partner in this. Looking at Center for Collective Impact for Earthquake Science. Collective impact is a new way of doing science, because right now we have our silos. You have the scientists, you have your engineers, you have the public. And these stakeholders aren't really working together. And one of the ways to kind of address that is by using collective impact. So what we're trying to look at for collective impact, or like challenges, we have to look at what we call high impact understudied. So basically everything that's in US terms, anything that's not California, Alaska, or the West Coast. Basically all of us are grouping together to kind of create a common agenda to say, yes, we need these work on this work looking at ground motions in Puerto Rico, but Utah and Texas have the same issues. So how can we work together? So right now it's being organized at UTEP. The outcomes are hoping to have more community resilience, improved scientific understanding of our earthquake processes, and broader participation in the science. And then how do we get the ground motion information to you as the engineers? And what information do you want from us as a geoscientist? So if you want more information, we have a couple QR codes, one to our webpage, and we do also have a podcast. If you want to learn about the scientists, I encourage you guys to listen to the podcasts. So this is just a coming attraction, so feel free to check those out. I wanted to kind of end with like just this ending slide to kind of say, we're talking about geology, the present is the key to the past. This is a quote from Charles Lyell, Principles of Geology. But we talk about earthquake and tsunami hazard. We have to look at the past as the key to our present and to our future. So thank you. Right now, we don't have, I'm working on making that model right now. So I'm hoping that by the end of this year to have the PTHA assessment done with Hongqi. And then getting into the engineering is the next step. And I wanted to advertise that this is being done on the science side. So you as engineers can, I'm hoping to interface here today to figure out how do we get the PTHA from the work I've been doing into the hazard, yeah.
The other question I would have is that the Seismological Society of America last year had their meeting here. One of the good things of that meeting was the Bruce Bolt Medal that Martinez Cruzado received. Did you see anything else in that event that was, really important to all this work for seismicity in Puerto Rico?
I'll be honest, I was the one organizing the event, so I essentially didn't get to see that much science. I'll be honest, because I was spending more time talking to people. I think the biggest thing coming out of that meeting is getting interest in doing more science in Puerto Rico. So one of the big things we got was more interest from our colleagues in the mainland to work here. Because the reality is we only have, 3 of us in UPRM? And we also have responsibilities for network operations and other responsibilities. So we're getting more bodies on the ground. That's probably the key thing.
Oye, después del terremoto, me tocó inspeccionar, y me imagino que unos colegas aquí también me tocó inspeccionar propiedades en Utuado. Y la verdad que impresiona Utuado, ¿sabes? Cuando me llamaron originalmente, pero sí tembló en abajo, que tiene que ver Utuado con el asunto. Y la realidad del asunto que fue fuerte, ¿sabes? Tengo estructuras que son federales, que se movieron bastante, ¿sabes? Bien diseñadas. Entonces yo veo que ustedes están trabajando mucho en el asunto. Yo creo que como comunidad científica y de ingeniería debemos reportar esto a la comunidad y tratar de identificar allá qué está pasando, porque esa comunidad es bien vulnerable, tiene gente muy de escasos recursos y que ha sufrido bastante, ¿verdad? Y Yo creo que se deberían enterar ellos mismos que están en una posición incómoda donde viven, ¿verdad? Porque no importa que tiemble en el sur o tiemble en el norte, se van a ver afectados por la situación que viven, ¿verdad? Yo creo que la exhortación también, Pepe, está en la comisión ahora, que se le notifique a la prensa, que se notifique a la gente, no sé, de forma de alarma no, ¿verdad? Porque no es una forma alarmante, pero que logremos que esa comunidad se entere que tiene un problema, porque ni ellos mismos entienden lo que está pasando en Utuado. No sé si los estudios que ustedes están haciendo allá en el sur tienen planes de hacerlos en la montaña de alguna manera para identificar cuáles son las zonas más vulnerables de Utuado.
Sí, muchísimas gracias. Yo creo que la contestación, yo creo que Elizabeth puede contestar mejor eso. Pero bueno, la situación es que nosotros estamos mirando ahora fallas activas. Definitivamente todos nos vamos a afectar, pero hay ciertos lugares que se van a afectar más debido a pues, la geología que tenemos. O sea, básicamente Utuado es como si fuera un bowl de gelatina. Tan pronto llegue esa onda sísmica ahí, la va a concentrar. Definitivamente trabajar con la comunidad, saber qué esperar es sumamente importante. Pero en términos de buscar fallas y ver la potencia que tiene, el potencial que tiene para generar eventos sísmicos, pues entonces ya... Pero empezamos por la parte suroeste porque es antes, desde los 70 se están observando, desde que tenemos actividad, redes sismológicas, poder determinar que dentro de Puerto Rico es el lugar donde más actividad sísmica existía ya. Así que sí.
Para energía en Utuado probablemente es un factor de amplificación. El suelo en el sitio que ya tenemos datos en UPR, Utuado, donde tenemos la estación sísmica, creo que es clase C, pero vamos a ir lunes a la escuela con daños para ver qué es el suelo. Yo creo que es un factor de amplificación de topografía, amplificación de suelo y basin effects, que se llama con la lata de sedimento. Pero para entender todo necesitan hacer estudios específicos de Utuado para entender qué es la profundidad de sedimentos y cuando tenemos esa profundidad y el tipo de suelo, pueden crear un modelo de tres dimensiones para entender qué pasó cuando una onda sísmica entra. Porque yo creo que la onda sísmica puede entrar, pero no puede salir del basin de Utuado. Pero necesitan los datos de sedimento y después un modelo para ver si es la verdad o no.
Thank you very much. Big round of applause.